Dear colleagues, good day. Let me propose my presentation with the topic optimization calculation of Vortex type granulation devices, application of software products and computer modeling. This material is a result of collective work of scientists of Sumy State University and Alexander Dubček University of Trenčín. Flows of single-phase and multi-phase medium play a key role in the working processes in many engineering devices. The design of these devices for the required operation parameters is impossible without a reliable prediction of the characteristics of these flows. Because of nature of these environments, flow of liquids and gases occur in complex manner to form non-stationary effects, dead zones, and vertex structures. These factors lead to growing interest of mathematical modeling tools for flows motion, which allow to predict the flow characteristics and parameters of the devices at design stages. Software can adequately simulate the complex physical effects taking place in flows motion in vertex granulator and perform calculation of flows within the reasonable time. This software provides convenient tools of data preparation and analysis of calculation results and are a powerful tool for accurately predict the characteristics of flows. Methods of computational fluid dynamics suggest calculation of flows through the numerical solution of equations of Navier-Stokes and continuity, describing the most general case of this medium motion. For turbulent flows, these are Reynolds equations. The purpose of work is creation of Vortex granulation optimization calculator algorithm. The author's software and calculation data visualization using software for calculation flows hydrodynamics should be created on the base of suggested algorithm. The scheme of the working space of Vortex granulator and design grid for modeling are shown in figures 1 and 2. Given that in practice, interest is usually deals with non-instantaneous, but the average in time velocity value for mathematical description of turbulent swirling motion of gas flow, as I said before, Reynolds equation as modification of Navier-Stokes equations are used. The Reynolds equation system is supplemented with flow continuity equation. Numerical solutions of mathematical model equations is performed in one matching passage from the working volume inlet cross-section to outlet using finite volumes method with the elements of finite element approach. Before calculating, the estimated grid is constructed as at figure 2, and unknown values of velocity and pressure are found in the nodes of this grid. The program conical channel is designed to calculate axial symmetric gas flow motion in channels, including the swirling flows in the diffuser. Initial data for calculation are geometric configuration of channel properties and parameters of gas flow in the inlet cross-section. The calculation objective is to determine the field of velocity and pressure in full range of calculated area and determination of energy losses between the inlet and outlet cross-section of channel. The program displays the calculation data as graphic dependencies. Program work starts with opening or creating new file of calculated area configuration. Example of calculation area configuration is shown in figure 3. After selecting the necessary parameter for calculation, program builds estimated grid. For the analysis of motion velocity components, it's necessary to define the nature of dependencies graphical components and match them within a comparative graph as it's shown in figures 4, 5, and 6. For research results visualization in this study, we also have used complex ANSYS CFX, which allows to export results, which was obtained in conical channel software. The main results of visualization are shown in figures 7 and 8. The value of gas flow radial velocity received by the results of analytical solution and experimental data have high degree of compliance. There is mutual deviation numerical value of speed and overall graphic image of diagrams of full speed radial component of gas flow has the same character. It's mentioned even radial velocity decreasing from the center of gas flow to the periphery. In general, in the following functional dependencies, for each component of gas flow velocity, it's observed in the same quality pattern. For rate and radial velocity components of gas flow for initial condition and changing set of geometrical and technological conditions does not cause such significant change of quantitative distribution value along the radius and height for both angular velocity component gas stream. Based on the analysis of hydrodynamic properties of gas flow due to certain variables, the rational selection of geometry, workspace, granulator becomes possible. Analysis of simulation using visualization software on CCFX has showed as follows. Depending on gas flow velocity component value, trajectory of its movement has different configuration with the predominance of one or another direction. When velocity axial component predominates, the area of gas flow movement is narrowed. When velocity circular component predominance, we observe an increased zone of gas flow vertex motion in height. When velocity radial component predominates, gas flow movement to the wall of vertex granulator is made more intense. Under certain conditions, the intensity of gas flow initial twisting does not affect the trajectory of its movement and affects only the value of gas flow resulting velocity. Velocity radial component is characterized by maximum value on the axis of the device. Simulation results allow us to develop an algorithm for vertex granulator hydrodynamic calculator, which is represented on figure 9. Simulation results. Example of granulator, which was designed based on the hydrodynamic calculation for production of porous ammonium nitrate with final product performance 3,000 kilograms per day, commodity fraction with granulars between 2 and 3 millimeters is shown in figure 10. This work was carried out under the project small-scale energy-saving modules with use of multifunctional devices with intensive hydrodynamics for the production, modification, and encapsulation of granules. My scientific part of report is complete. At the end of my speech, I want to wish you good health. I am sure that we will have the opportunity to meet each other and shake hands in the nearest future. Thanks you very much and good luck.